Welcome to the deep dive. Today, you're joining us for quite a journey, actually. We're going from our little corner of space right down to the Earth under our feet.
This is right. We're digging into Earth Science, second edition, the QuickStudy Academic Guide, to pull out the really essential stuff.
Yeah, the goal is to give you the big picture, the most fascinating bits about Earth and, its place in the cosmos without getting lost in the weeds.
Exactly. Think of it as connecting the dots from the sun's core to Earth's oceans, how it all links together through these fundamental forces. We're aiming for those aha moments, those surprising facts.
Okay, let's jump right in then. The sun, our star.
The big one.
Ha, yeah, understatement. The guide starts with this fact that just floors me, 99.8%.
99.8% of the mass of the entire solar system.
So everything else, I mean, Jupiter, Earth, all the asteroids, moons, it's basically just noise in the data.
Pretty much. It's almost negligible compared to the sun's mass. And that mass, well, that dictates everything, gravitationally speaking.
Right, it holds the whole thing together. And it's been doing that for, what, 4.6 billion years?
Around that, yeah. And it's got plenty left in the tank, probably another 5 billion years or so in its current state.
Wow, 5 billion. And the energy source for all that time is nuclear fusion, right? Hydrogen smashing into helium.
That's the engine. Down in the core, incredible pressure and temperature forcing hydrogen atoms together to make helium and releasing just immense amounts of energy in the process.
And that energy is ultimately what powers almost everything here. Sunlight, obviously, but also indirectly.
Oh, completely. Wind, fossil fuels, which are basically stored ancient sunlight, the water cycle. It all traces back to the sun.
Now, when we look at it, it seems like this, steady ball of light. But the guide stresses it's actually pretty dynamic.
Very dynamic. You've got sunspots, for instance. They look dark, but they're actually areas of intense magnetic activity.
Yeah.
Cooler than the surroundings, but magnetically powerful.
Those magnetic fields can cause solar flares, those massive eruptions.
Exactly. Huge bursts of energy and charged particles flung out into space. And those can definitely have effects here on Earth. Mess with satellites, power grids, that sort of thing.
And then there's the corona, that sort of outer atmosphere, super hot plasma.
Incredibly hot, millions of degrees. You really only see it clearly during a total solar eclipse.
Yeah.
It's that spectacular halo around the blocked out sun.
Amazing. And the light itself, it's not just visible light, is it? There's a whole spectrum.
Right. And by analyzing that spectrum, slitting the light into its different wavelengths, scientists can figure out what the sun is made of. It's like reading its chemical signature from millions of miles away.
Like a cosmic barcode. So how much of that energy actually reaches us?
On average, about 120 watts per square meter per day hits the top of our atmosphere. Doesn't sound like a huge number, maybe, but it powers everything.
Yeah, from the seasons, because of Earth's tilt relative to the sun, to, well, solar panels converting it directly.
And even the colors we see, the visible spectrum, that rainbow from about 400 to 700 nanometers, when you look closely at sunlight that's passed through our atmosphere, you see these dark lines, absorption lines.
Where specific wavelengths have been soaked up by molecules in the air.
Precisely. Tells us about our own atmosphere, too. And then beyond the visible, you've got ultraviolet, the UV radiation.
The stuff that gives you sunburn.
Yeah, that's the one. Wavelengths from 10 to 400 nanometers. Luckily, our ozone layer in the stratosphere absorbs most of the really harmful UV.
A crucial shield. Okay, so that's our sun. What about other stars? The distances are just mind-boggling.
They really are. We measure them in light years. You know, the distance light travels in a year, which is about 9.5 trillion kilometers.
Trillion, wow. Or parsecs, that's another unit.
Yep, a parsec is about 3.26 light years. That's what astronomers often use. Our nearest neighbor, Proxima Centauri, is just over 4 light years away.
Still sounds incredibly far. And most stars we see at night, they're relatively close.
Relatively, yes. Most naked eye stars are within about 500 parsecs. Gives you a sense of our local galactic neighborhood.
And our sun, it's considered a pretty average star, right? A main sequence star.
Yeah, typical main sequence star, happily fusing hydrogen into helium. It's doing its thing.
But not all stars are the same size or live the same lives. There's a link between how hot they are and how long they last.
Absolutely. The bigger and hotter a star is, the brighter it shines, but the faster it burns through its fuel. They live fast and die young, cosmically speaking.
So what happens at the end? Small stars just sort of fade out.
Pretty much. Stars like our sun, or a bit smaller, when they run out of hydrogen fuel in their core, they eventually shed their outer layers, and the core collapses into a white dwarf. Very dense, about the size of Earth. A quiet end.
But medium-sized stars, like our sun eventually, They puff up first.
They do. They start fusing helium into carbon, which makes them expand dramatically into red giants, and then into what's called an asymptotic giant branch star, even bigger and brighter.
Okay, but the really big ones, they go out with a bang.
Oh yeah, supernova. Massive stars fuse heavier and heavier elements until they get to iron and nickel in the core. Fusion stops there because fusing iron actually consumes energy instead of releasing it.
Uh-oh.
Exactly. Gravity wins. The core collapses catastrophically, rebounds, and the star blows itself apart in a supernova explosion.
And that's where the heavy stuff comes from. Gold, silver, uranium.
That's the main source. These explosions are the cosmic forges for elements heavier than iron. So the iron in your blood, the gold and iron, it was likely created in a supernova billions of years ago. We're literally made of stardust.
That is incredible. And what's left behind after the explosion?
Depends on the mass. Could be an incredibly dense neutron star, basically a giant atomic nucleus the size of a city, or if the original star was massive enough, a black hole. Gravity's so strong nothing escapes, not even light.
Wow, and the debris from the supernova, it doesn't just disappear.
Nope, it forms nebulae, these vast, beautiful clouds of gas and dust. And these nebulae are the stellar nurseries where new stars and planetary systems are born. It's a cycle.
A cosmic recycling program. And stars often form in groups, right? Clusters.
They do. Stars born from the same nebula often stay gravitationally bound together in clusters for a while. Though our sun seems to be a bit of a loner.
Yeah, I was surprised the guide said about half of all stars are actually in multiple systems, binaries, or even more.
Binary stars are very common. Two stars orbiting a common center of gravity. We can spot some visually. Others, by the way, their light spectra shift as they orbit spectroscopic binaries. And yeah, you can get triple, quadruple systems, complex gravitational dances.
Okay, zooming out even further. Galaxies. Huge collections of stars.
Billions, even hundreds of billions of stars, plus gas, dust, dark matter, all held together by gravity. And they come in different shapes.
Like ellipticals, which are kind of round or squashed spheres.
Right. And spirals, like Andromeda, with those beautiful arms winding out. And barred spirals, where the arms start from a central bar structure.
Which is what our Milky Way is, right? A barred spiral.
Yep. Our home galaxy contains maybe 200 billion stars, give or take. It's about 130,000 light years across. And we're located out in one of the spiral arms, the Orion arm, kind of in the galactic suburbs.
Oh, galactic suburbs. I like that. And the Milky Way isn't alone either. It has smaller galaxies orbiting it.
It does, dwarf galaxies. The Large and Small Magellanic Clouds are the most famous ones, visible from the southern hemisphere. They each have billions of stars, too.
And we're part of a group of galaxies, the local group.
That's us. Dominated by the Milky Way and the Andromeda Galaxy, plus dozens of smaller ones. And these groups are clumped together into even larger structures, galactic clusters and superclusters. It's structure all the way up.
Like cosmic Russian dolls. And the sheer number of galaxies out there, the estimate is huge.
Astronomical. Estimates range from maybe 125 billion up to possibly 2 trillion galaxies, just in the part of the universe we can observe. It's humbling.
It really is. And the universe itself is expanding.
It is. Edwin Hubble discovered that galaxies are generally moving away from us, and the farther away they are, the faster they're receding. Hubble's law.
And we know this because of redshift. The light gets stretched.
Exactly. As objects move away, the wavelengths of their light get stretched out, shifting towards the red end of the spectrum. The amount of redshift tells us how fast they're receding.
Okay, mine's sufficiently blown by the cosmic scale. Let's pull our focus back home to our solar system, our neighborhood, planets.
Right. These are bodies that orbit a star, don't produce their own light, but shine by reflecting the star's light. And most in our system orbit in roughly the same plane, the ecliptic.
And they all formed around the same time as the sun, from that same cloud of gas and dust.
Pretty much, yeah. Leftover material from previous stars. And our solar system has different flavors of planets.
Yeah, the guide breaks them down. First, the rocky ones, the terrestrial planets, like Earth, Mars.
Small, dense, solid surfaces, made mostly of silicates and metals. Not much hydrogen or helium compared to the outer planets.
Then, dwarf planets, like Pluto. Solid, but smaller, less dense, more ice.
That's the idea. Ceres in the asteroid belt is another example. They haven't quite cleared their orbital neighborhood like the main planets have.
Okay. Then the giants, gas giants first. Jupiter, Saturn.
Huge. Mostly hydrogen and helium, just like the sun, really. No solid surface to speak of. They just get denser and denser towards the core.
And then the ice giants, Uranus and Neptune. Still big, but different composition.
Yeah, they have hydrogen and helium, but also a lot more Ice is water, methane, ammonia. Still no solid surface, but a different internal mix than the gas giants, and bigger than the rocky planets, of course.
And now we know these aren't the only types of planets out there. Exoplanets, orbiting other stars.
A whole new universe opened up there, starting seriously in the 1990s. We find them in a few ways. Sometimes by seeing the star's light dim just a tiny bit as the planet passes in front of the transit method.
Like a mini eclipse.
Exactly. Or by detecting the slight wobble of the star caused by the planet's gravity pulling on it the radial velocity method.
And we're finding them everywhere, even in habitable zones.
We are finding planets in that zone where liquid water could potentially exist on the surface. The diversity is amazing too. Planets orbiting in hours, planets taking centuries, sizes from smaller than our moon to way bigger than Jupiter.
And even rogue planets just wandering between stars.
Seems so. Planets ejected from their systems, perhaps. It's an incredibly active field of discovery right now. Every week, almost, new finds.
And planets aren't the only things orbiting. Moons, natural satellites.
Loads of them. They range from tiny captured asteroids, maybe just a few kilometers across, to monsters bigger than the planet Mercury, like Jupiter's Ganymede or Saturn's Titan.
The big ones are around because of gravity, right?
Yep, their own gravity pulls them into a spherical shape, and some are surprisingly active geologically. We think Jupiter's moon, Europa, and Saturn's moon, Enceladus, might have liquid water oceans beneath their icy shells.
Liquid water, that's huge for the possibility of life. And Titan has a thick atmosphere.
Thicker than Earth's, mostly nitrogen and methane. This is a fascinating world.
So much variety. Now, all this orbiting, it follows rules, laws of physics. Started with Copernicus, right? Bringing back the sun-centered idea.
He really pushed the heliocentric model, yeah, building on ancient Greek ideas like Aristarchus's. But it was Johannes Kepler who figured out the details of how they orbit.
Kepler's laws. Okay, number one. Orbits are ellipses, not perfect circles, with the sun at one focus.
Correct. Number two, a planet moves faster when it's closer to the sun and slower when it's farther away. It sweeps out equal areas in equal times.
Right, that variable speed thing.
Right.
And number three connects the orbital time, the period, to the size of the orbit.
Precisely. The square of the orbital period is proportional to the cube of the semi-major axis, which is basically the average distance from the sun, and eccentricity measures how squashed that ellipse is.
Got it. Then Newton came along and explained why they move like that. Gravity.
Newton's law of universal gravitation. That fundamental force between any two objects with mass, stronger with more mass, weaker with more distance, that inverse square law. It explained Kepler's laws perfectly.
And even Newton isn't the final word. Einstein's general relativity gives a deeper picture and predicts gravitational waves.
It does. Describes gravity not as a force, but as the curvature of space-time caused by mass and energy. And yeah, it predicted these ripples in space-time, gravitational waves, caused by things like merging black holes or neutron stars.
And we actually detected those, LIGO, right, in 2015.
That was it. A monumental discovery confirming Einstein and opening a whole new way to listen to the universe.
Amazing. Okay, let's zero in completely now. Earth, our home, third rock from the sun.
1 astronomical unit, or AU, about 150 million kilometers away. Takes us 365.25 days to go around once. That's our year.
And we spin on our axis every 24 hours, giving us day and night. And that tilt, about 23 degrees. That's key, isn't it?
Absolutely crucial. That axial tilt is why we have seasons. As we orbit, different parts of the Earth get more direct sunlight, leading to summer and winter. Without the tilt, climate would be drastically different.
And size-wise, about 12,600 kilometers in diameter. And we have our own companion, the moon.
Our moon. 5th largest in the solar system, but unusually large compared to its planet, orbits us about every 28 days.
Giving us the phases of the moon. And its gravity causes tides.
Primarily tides, yeah. Pulls on Earth's oceans, also causes a slight wobble in Earth's rotation. And it's tidally locked, so we always see the same face.
Right, the man in the moon side. And it's covered in craters because no atmosphere.
Exactly. No atmosphere to burn up incoming meteoroids and no weather or geological activity to erase the impact scars. It's a record of ancient bombardment, and no surface water, of course.
Okay, let's go inside Earth now. What's down there? Layers, right?
Yep. Outermost is the crust. Relatively thin, 5 to 70 kilometers thick. Mostly silicate rocks. Thicker under continents, thinner under oceans.
Below that, the mantle.
Huge layer. Nearly 3,000 kilometers thick. Made of denser silicate rocks, rich in iron and magnesium. It's hot enough that it can flow very slowly, like super thick tar. That flow drives plate tectonics.
And below the mantle, the core.
2 parts. The outer core is liquid, mostly iron and nickel. Hot, churning liquid metal.
And the inner core, solid, even though it's hotter.
Solid, yeah. The immense pressure down there keeps it solid despite the heat. Also, mostly iron and nickel.
And that liquid outer core is responsible for Earth's magnetic field, the dynamo theory.
That's the leading theory. The combination of the churning, electrically conductive liquid iron plus Earth's rotation generates a powerful magnetic field that extends way out into space. Our protective shield.
Incredible, a planet-sized generator. Now, looking back, Earth's history is long. How old are the oldest rocks we've found?
About 4 billion years old. We figure out these ages using radioactive dating, measuring the decay of certain isotopes in the rocks.
And life started pretty early on.
Seems so. Earliest evidence, maybe fossilized microbial mats called stromatolites, goes back at least 3.7 billion years. Maybe even earlier. Life got a foothold relatively quickly after the planet cooled down.
So single-celled life dominated for billions of years during the Archean. Then photosynthesis changed everything.
Big time. Cyanobacteria started producing oxygen as a byproduct. It took a long, long time, but eventually it built up in the atmosphere, paving the way for more complex life.
First, multicellular life, around 640 million years ago, then the Cambrian explosion.
Yeah, around 540 million years ago, there was this relatively sudden burst of diversification. Lots of major animal groups appeared in the fossil record quite rapidly, a really key event.
Then the Paleozoic era. Lots happening there, life moving onto land, but ending in the massive extinction.
The Permian-Triassic extinction, yeah. About 250 million years ago, the biggest one we know of. Wiped out something like 95, 97% the marine species. Huge losses on land, too. Really reshaped life on Earth.
And fossils are a window into all this. Preserved remains.
Or traces, like footprints. They're invaluable evidence of past life and environments.
After the big extinction came the Mesozoic era, the age of reptiles, dinosaurs.
That's the one. From 250 million down to 66 million years ago, dominated by dinosaurs on land, marine reptiles in the seas, pterosaurs in the air, ended abruptly, most likely with that big asteroid impact of the Yucatan.
Wiped out the dinosaurs except for birds and paved the way for mammals, the Cenozoic era.
Exactly. The last 66 million years.
Yeah.
Mammals diversified and filled many of the niches left vacant. Within the Cenozoic, we have the Quaternary period, the last couple of million years, marked by cycles of ice ages.
And we're currently in the Holocene epoch since the last ice age ended.
Yep, last 11,000 years or so. Covers all of recorded human history, saw the extinction of many large ice age mammals, and, well, here we are.
What a history. And underpinning so much of it is the movement of the continents themselves, plate tectonics.
The grand unifying theory of geology, really.
Yeah.
The idea that Earth's outer rigid layer, the lithosphere that's the crust, plus the very top part of the mantle, is broken into these large plates.
And these plates are moving around, floating on the layer beneath.
On the asthenosphere, yeah. It's a hotter, weaker, more easily flowing part of the upper mantle. The plates slowly drift across it.
And the evidence for this, continents fitting together like puzzle pieces.
That was an early clue, yeah. Alfred Wegener pointed that out. Plus, identical fossils found on continents now separated by vast oceans, similar rock types lining up across oceans.
And paleomagnetism, the Earth's ancient magnetic field recorded in rocks.
That was a clincher. Rocks lock in the direction of Earth's magnetic field when they form. By studying old rocks, scientists could track how continents had moved relative to the magnetic poles. It also showed the magnetic field has flipped polarity many times in the past.
Wow. So how do these plates interact at the edges?
Different ways. Subduction is where one plate slides underneath another. Often happens when dense oceanic crust meets lighter continental crust. Creates deep ocean trenches and volcanic mountain ranges, like the Andes.
Okay. What about when they pull apart? Rifts?
Yeah, like the Mid-Atlantic Ridge or the East African Rift Valley. Magma wells up from below to create new crust as the plates separate.
And when continents collide head-on.
Big pileup. The crust buckles, folds, fractures, gets pushed upwards. That's how massive mountain ranges like the Himalayas formed when India slammed into Asia.
And sometimes they just slide past each other.
Strike-slip faults. The San Andreas Fault in California is the classic example. Plates grinding horizontally past one another. And a fault generally is just any significant break in the rock where movement has occurred.
All this movement, that's what causes earthquakes, right?
Primarily, yes. The sudden release of built-up stress along these plate boundaries, or faults. The ground shakes, as seismic waves radiate outwards.
P waves and S waves, primary and secondary.
Those are the main body waves that travel through the Earth. P waves are compressional, like sound waves. They arrive first. S waves are shear waves, shaking side to side. They arrive second and can't travel through liquids, like the outer core.
And the epicenter is the spot on the surface directly above where the quake starts.
Right, above the focus or hypocenter.
Mm-hmm.
And we measure the energy released using magnitude scales, like the Richter scale, though others are more common now. It's logarithmic, so each whole number increase means about 32 times more energy.
A big jump. Okay, from shaking to erupting. Volcanoes, openings where magma reaches the surface.
Magma below ground, lava once it erupts. Yeah. Lots of volcanic activity happens underwater at those mid-ocean ridges where plates pull apart.
And on land, different types. Shield volcanoes.
Broad, gentle slopes built up by fluid lava flows like in Hawaii. Cinder cones are smaller, steeper, made of ejected volcanic fragments.
And composite volcanoes, stratvolcanoes, like Mount Fuji or Rainier.
Tall, cone-shaped, built from alternating layers of lava flows and ash or pyroclastic material, often have more explosive eruptions.
Some volcanoes aren't even at plate boundaries. Hotspots.
Like Hawaii or Yellowstone, believed to be caused by plumes of extra hot material rising from deep within the mantle, punching through the plate above it.
And what comes out? Lava, gas.
Lava, gases like water vapor, CO2, sulfur dioxide, pulverized rock, volcanic glass, ash. The type of eruption depends a lot on the magma's composition, temperature, and gas content. Viscous, gassy magma tends to erupt more explosively.
And we see volcanoes elsewhere in the solar system, too.
Oh, yes. Mars has the largest volcano, Olympus Mons. Jupiter's moon Io is incredibly volcanically active. Evidence on Venus, maybe even Mercury.
And old volcanic areas leave behind features. Necks, craters, calderas.
Yeah, volcanic necks are the solidified plumbing inside an eroded volcano. Craters are the summit depressions. Fissure eruptions are lava flowing from long cracks. And calderas are large collapse features formed after huge eruptions empty the magma chamber below.
Okay, shifting gears from fire to water, the blue planet. Oceans cover most of it.
About 70% of the globe, and hold 97% of Earth's water. Vast.
And they're zoned by depth and light from the sunny surface layer.
The epipelagic zone, down through the mesopelagic, twilight zone, bathopelagic, midnight zone, abyssal, deep ocean floor, and finally the hadopelagic zone in the deepest trenches. Life adapts to incredible pressure and darkness down there.
And the water's always moving. Currents.
Huge systems of currents driven by wind, differences in temperature and salinity, and the Coriolis affect Earth's rotation, deflecting the flow. They're incredibly important for distributing heat around the planet, regulating climate.
Salinity. That's the saltiness, mostly sodium chloride.
Primarily, yes, plus other dissolved ions. Average ocean salinity is about 3.5% or 35 grams per liter. Way too salty to drink. Fresh water is less than 0.05%. Brackish water in estuaries is in between.
And places like the Dead Sea are super salty because of evaporation.
Exactly. Water evaporates, leaves the salt behind, concentrating it over time.
And coasts, the boundary zones, shaped by tides.
Tides, driven mainly by the moon's gravity, play a huge role in coastal ecosystems and processes. And the sheer volume of water moderates coastal climates, keeps them from getting extremely hot or cold.
All this water is constantly cycling, right? The water cycle.
The hydrologic cycle, yeah. Evaporation powered by the sun lifts water vapor into the atmosphere. Winds move it around. Condensation forms clouds. Precipitation brings it back down as rain, snow, etc.
Then it flows back to the sea or soaks into the ground and starts over.
But that's the loop. It's a dynamic balance. On average, more water falls on land than evaporates from it, and the reverse is true over the oceans. River runoff balances it out.
And moving water. Rivers and streams. They do a lot of work shaping the land.
The most important agent of erosion by far. The flow is affected by friction with the channel, and the gradient, the steepness of the slope.
Steeper slope means more energy, faster flow.
Generally, yes. Though discharge, the volume of water flowing, also plays a huge role. A river's profile usually flattens out as it approaches its mouth, near base level.
Base level, the lowest point it can erode down to, usually sea level.
Sea level is the ultimate base level for most rivers. Lakes, or resistant rock layers, can act as temporary local base levels. Changes in base level really affect how a river erodes or deposits sediment.
And how do streams carry material?
3 ways. Dissolved load, ions in solution, suspended load, fine particles like silt and clay carried along in the water, and bed load, larger sand and gravel bouncing or rolling along the bottom.
Plus mass wasting, landslides, mud flows.
That's gravity pulling material downhill directly. Water often plays a role in triggering it, though. The angle of repose is the steepest slope loose material can hold without sliding.
And competence and capacity, what are those?
Competence is the maximum size of particle a stream can move, related to its velocity. Capacity is the total amount of sediment it can carry, related to its discharge.
When the water slows down, it drops the sediment. Largest stuff first.
Yep, that's deposition. Leads to sorting, where sediments of similar size get deposited together. Alluvium is the general term for stream-deposited sediment. Deltas form at the mouth where velocity drops dramatically.
And rivers build their own banks, natural levees.
During floods, yeah. As water overflows the channel, it slows down and drops coarser sediment right along the banks, building them up over time. Can lead to back swamps behind the levees and weird parallel tributaries called Yazoo streams.
Valleys can be V-shaped or wide and flat.
V-shaped valleys indicate the river is mainly cutting downwards. Wider valleys with floodplains mean the river has been meandering side to side, doing more lateral erosion. Resistant rock layers can create rapids and waterfalls.
And meanders. Those big river bends, they can get cut off.
They can. Erosion happens fastest on the outer bend, deposition on the inner bend, point bars. Over time, the loops get more exaggerated, and eventually the river might cut straight across the neck of a loop, forming an oxbow lake. The meanders slowly migrate downstream, too.
And the pattern of rivers on the landscape tells you something. Drainage patterns.
Can give clues about the underlying geology. Dendritic, tree-like, is common on uniform materials. Radial flows off a central high point. Rectangular follows joints or faults in bedrock. Trellis develops in areas of folded rock layers.
Okay, what about water under the ground? Groundwater.
Huge resource. Water filling the pore spaces in soil and sediment and fractures in bedrock. It's the largest accessible reservoir of fresh water. Supplies drinking water for about half the world's population.
The top of the saturated zone is the water table.
Right. Above it is the unsaturated zone, or zone of aeration. Sometimes impermeable layers can trap pockets of groundwater above the main water table, called perched water tables. Aquifers are permeable layers that transmit groundwater easily.
And groundwater keeps streams flowing even when it's not raining.
Absolutely vital for that, especially during dry spells. Base flow from groundwater discharge.
But we can use too much. Depletion and contamination.
Big problems in many areas. Overpumping lowers the water table, can cause land subsidence, damage infrastructure, form sinkholes. Contamination from agriculture, industry, sewage is a major concern because cleaning it up is difficult and slow. Some rocks filter better than others.
Springs are where groundwater comes out naturally. Wells are where we drill down.
Exactly. Artesian wells tap into confined aquifers where pressure forces water to rise. Pumping creates a cone of depression, lowering the water table around the well.
Hot springs and geysers, related to volcanic heat.
Usually, yeah. Groundwater heated by proximity to magma or hot rocks. Geysers are like intermittent hot springs that erupt periodically.
And caves, often formed by groundwater.
Many are solutional caves, formed over long periods as slightly acidic groundwater, dissolves soluble rock like limestone. You also get lava tubes, sea caves, glacial caves. Stalactites hang from the ceiling, stalagmites grow from the floor.
Okay, moving upwards now. The atmosphere, the air around us.
That blanket of gases, mostly nitrogen, 78%, and oxygen, 21%, plus argon, a variable amount of water vapor, a tiny bit of CO2, and trace gases. It exerts pressure, which decreases rapidly with altitude.
And it has layers too. Troposphere is where we live, where weather happens.
That's the lowest layer, densest, holds most of the water vapor and clouds. Above that is the stratosphere, which contains the ozone layer. Jets fly near the top of the troposphere, or lower stratosphere.
Then mesosphere, thermosphere, exosphere are going outwards.
Right, getting thinner and thinner. The ionosphere isn't really a distinct layer by temperature, but a region overlapping the upper layers where solar radiation ionizes atoms. That's where auroras happen, and it affects radio waves.
And within the troposphere, wind. Air moving because of pressure differences.
Driven by uneven solar heating, basically. Air moves from high pressure to low pressure, but Earth's rotation, Coriolis effect, deflects it. Gusts are short bursts. Sustained winds are what we usually measure.
Jet streams. High altitude, fast winds.
Rivers of air near the top of the troposphere, generally flowing west to east. They steer weather systems. We also have large-scale global wind patterns, like the trade winds and westerlies, and local winds like sea breezes and mountain breezes, driven by daily heating differences.
And clouds. Tiny water droplets or ice crystals.
Formed when air cools and water vapor condenses onto tiny particles. Classified by their form-layered stratus, puffy cumulus, wispy cirrus, and their altitude, high, middle, low, or multi-level, like storm clouds.
Meteorology. The study of weather, short-term conditions.
Yeah, temperature, wind, precipitation, pressure. measured with instruments like thermometers, anemometers, barometers, rain gauges. Meteorologists use this data, plus computer models and historical patterns, to make forecasts, vital for farming, aviation, safety.
And climate is the long-term picture. Average weather over decades.
Right. What's typical for a region? Influenced by latitude, altitude, proximity to oceans, ocean currents, mountains. El Niño and La Niña are examples of natural climate variations in the Pacific that have global ripple effects every few years.
And we can study past climates through ice cores, tree rings.
Sediments, too, gives us context for current changes. A climate normal is usually defined as a 30-year average, and we know the global average temperature has risen significantly over the last century or so.
Which brings us to human impacts. CO2 from burning fossil fuels trapping heat.
The greenhouse effect? Amplified. And chemicals like CFCs used in old refrigerators and aerosols damage the ozone layer, creating that hole over Antarctica.
But the Montreal Protocol banned CFCs, and the ozone layer is recovering.
Slowly, yes. It's a success story for international cooperation. NASA thinks it might get back to pre-1980 levels, maybe around 2070. But the CO2 issue is obviously ongoing and complex.
Okay, last big topic, the stuff Earth is actually made of. Rocks and minerals. What's the difference?
A mineral is a naturally occurring inorganic solid with a specific chemical composition and a definite crystalline structure. Its atoms are arranged in an orderly, repeating pattern.
And we identify them by properties like luster, color, hardness.
Luster, how it reflects light. Color, can be tricky, variable. Streak, color of its powder. Hardness, using the Mohs scale, like does it scratch glass. Shape, crystal form or how it breaks cleavage or fracture. Specific gravity, density.
Most common minerals are silicates, based on silicon and oxygen.
By far the most abundant. Things like quartz, feldspar, mica, olivine. Huge variety of structures. Then you have non-silicates like carbonates, limestone minerals, oxides, iron ores, sulfides, sulfates, gypsum, halide salt, and native elements like gold or copper.
And rocks are made of minerals.
Usually aggregates of one or more minerals or sometimes mineral-like substances, classified by how they form into three main types: igneous, sedimentary, metamorphic.
Igneous, from cooled magma or lava.
Right. If it cools slowly underground, intrusive plutonic, it forms larger crystals like granite. If it cools quickly at the surface, extrusive volcanic, smaller crystals like basalt or rhyolite. Superfast cooling gives volcanic glass, obsidian. Texture tells you about cooling rate.
Metamorphic, existing rocks changed by heat and pressure.
Or chemical reactions. Doesn't melt completely, but transforms. Can happen near magma, contact metamorphism, or over large regions during mountain building, regional metamorphism. Can develop layers or bands, foliation like in slate or gneiss, or be non-foliated like marble or quartzite.
And sedimentary, from bits of other rocks cemented together, or chemical precipitation.
Yep. Weathering breaks down rocks, erosion moves the pieces, deposition drops them, and then compaction and cementation turn the sediments into rock. Detrital rocks are made of fragments like sandstone or shale. Chemical rocks form from dissolved substances precipitating out like limestone or rock salt, or from organic matter like coal. They often contain fossils and clues about past environments.
And these all connect. The rock cycle.
Absolutely. Any rock type can be transformed into any other rock type through geological processes like melting, erosion, heat, pressure. It's a continuous cycle of creation and transformation.
Wow. We covered an incredible amount of ground, from the sun's core to Earth's core, and out to the edge of the observable universe.
It really highlights the connections, doesn't it? How processes in stars create the elements that make up planets, how planetary dynamics influence climate and life.
Yeah, and how seemingly stable things, like our magnetic field, are actually the result of incredibly dynamic processes deep inside the Earth, that constant churning liquid iron core.
It's a powerful reminder that Earth is a living, breathing, constantly changing planet operating within this vast, evolving cosmos.
Definitely. It leaves you wondering, given all this constant change we've talked about on Earth and out in space, what kinds of transformations might lie ahead in the really deep future for our planet, or even just for our understanding of everything?
That's a great question to ponder. What does the long-term future hold? Considering things like the sun's own evolution or the continued movement of tectonic plates, food for thought.
Absolutely. Hopefully this deep dive has sparked your curiosity to keep exploring these amazing topics. There's always more to learn about our incredible planet and the universe it inhabits.